Okay. So this test is just going to be 4.1 and 4.2. Don't worry about it being a test. It's not going to be tough. It's not going to be any tougher than a quiz. Yeah, I'm going to call it this because we have to have one in before the end of the quarter to appease the. Yeah. So what you're going to have to know. Um, 4.1 definitions, theorems. Are there any corollaries? No, they're just definitions and theorems. Where I'm going to give you everything except a blank, right? I'm not going to expect you to know the whole definition or theorem, but everything except a blank, and you know how to fill it in. What's that?
Didn't you ask for a worksheet, like, so we can review worksheet stuff?
Yeah, but for these, you have a textbook at home. This is page 187 through. It's not bad. You just because they have them outlined and and I'll give you problems too. You can also, if you want to practice some problems, but in the yellow boxes, definitions and theorems, 187 through 190. So this is just section 4.1. Definitions and theorems. So an example, I'll just say it orally, would be on like 187. If I say I'll write exactly. So imagine this box exactly as it looks. It says definition. It says absolute extreme values, and I write let f be a function with domain D. Then f of c is the blank on D if and only if f of x is less than or equal to f of c for all x in the domain, capital D. Well, you know they're talking about absolute extreme values, so you know, okay, I have to memorize whether it's going to be, I'm filling in absolute max or absolute min. It's very straightforward, very simple, just leaving you a couple blanks that you fill in, absolute max or absolute min. Theorem 1 on the next page, page 188, the extreme value theorem. If I say if f is continuous on a closed interval a to b, then f has both a blank value and a blank value on the interval. Maximum, minimum. Right, nothing too scary that you have to. I'm not making you memorize the whole thing. Just try to memorize the whole thing, and then it's easy enough. Okay, I know what the blank is. 189, the definition of local extreme values. Again, I give you everything except probably what's highlighted. Blank at C if and only if da 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 da. Local max value versus local min value. F of C is the value when x is C, the value of the function x is C. So some point x equals C. Let C be an interior point, so a point within the interval, whether it be the entire domain or if they specify an interval. The next theorem, theorem 2, local extreme values. If a function f has a local maximum value or a local minimum value at an interior point C of its domain, and if f prime exists at C, then blank. What's that? F prime of C equals 0.
Can you explain
Explain theorem 2?
Yeah.
Okay, so local extreme values, when you set f prime of c equal to 0, when you say f prime of x equal to 0, I was saying, okay, give me the tangent, no, give me the point where the tangent line is horizontal.
Okay.
And that, of course, would be local extreme, because that's where we have that change in direction. Either it's increasing, then decreasing there, or it was decreasing and starts to increase there.
That makes sense.
Yep. Definition of a critical point on page 190, a point in the interior of the domain of a function f at which f prime equals 0, or I might make this a blank, or blank is a critical point of f. Or I might decide to say, okay, a point in the interior of the domain of a function f at which f prime equals 0 or f prime does not exist is a blank. which of course that'd be even way easier because the definition is called critical point. I'm probably going to make the one blank, either the part that says f prime equals 0 or f prime does not exist, one of those blank. But just know that critical points, either where the f prime equals 0 or where f prime does not exist for critical points. Just make sure you're solid on these. And then now find extreme values. So you would need to be able to find extreme values. So then you have to know how to go about doing that. And we looked at problems where we go about doing that. So just see an example. So when finding absolute extrema, make sure to check where f prime does not exist, f prime equals 0, and those two are specifically critical points. And then of course the endpoint.
How does finding f prime doesn't exist, how does that change a maximum?
It may point one out because think about a cusp. Oh, a cusp. Oh, okay. So that might be a local min, or if the cusp happens this way, that might be a local max. Same for a corner. Yeah. It may not be, but what you do is you figure out all the possibilities and then you compare them. So make sure you guys are clear on that, right? We figure out all these three possibilities, list all the points of where this occurs, and then compare all of them. Okay. The one that has the largest value. So let's see, we do this, you can find one.
So wait, this is like to check if the point is a max. And max and min can be told by the y values, right?
Yeah, the value of your extrema, that is the y value. That is the value if you evaluate for the original function.
Okay.
So let's be careful there. I'm going to pull up the notes from when we did that, and it was very clean looking. Let's see, 13, complex fraction, Rolle's theorem, secant line, extreme value theorem, finding extrema. Looks like this one here. So here's the big picture, how to find extrema, the three that I point out. These two are called critical points and endpoint values. So I'll give you an interval. There's two there. There may be none for these, but there may be several for this, none for this. There may be one for this, none for this. We have to do all. Okay, where is f prime equals 0? Where is f prime does not exist? Yes.
So I understand the first one, you find the derivative and you go to 0. And that's when you solve it. But how do you do where it doesn't exist?
Good question. So where it doesn't exist is when you have division by 0. Or an even root of a negative.
If at any point, if it doesn't exist, then...
Well, as long as it's within your interval. You don't care about issues that occur outside your interval.
But I want to. They're important too.
And then endpoint values. So this was a good example. So you might something like this on the test. F of x equals x to the 2/3. Something simple.
Yeah, so it's going to be a simple function. It's not going to be like what x is. But that one we have to do is.
Yeah, right. I'm not going to give you something. I'm not going to give you something crazy. I'm not going to give you an exponential. I'm not going to give you logarithmic.
Okay. Should we expect trig?
I'm going to give you something like this, or maybe a rational function. Probably not trig.
Okay.
Let's see.
But that is not a thing, right? Because we might do it on
because we can look at more complicated problems. Like I do say, we can look at more complicated problems as we get further into the year, get closer to okay. Now we're prepping for the AP exam. But here, the main concept I want to get is that you know the outline. Okay, I know what I'm looking for. That's really what I want to test you on. So something simple like this. This is a good review problem. F of x equals x 2/3. So f prime of x equals 2/3 x to the negative 1/3. And so now, trick here is again, write this as a positive exponent so you can clearly see, oh, division by 0 is an issue. So we know that f prime of 0 is undefined, or this is where f prime does not exist, is when x is 0. And that was number 2 in the step that I listed here, 1, 2, and 3. So where it doesn't exist, there's no value of x where f prime could be 0, right? There's no way this could be 0. So that's been done, taken care of. Here we found 1 point for this, and then the endpoint. So there's a total of 3 things that we are checking. We have this point here, which is from where it was undefined, 0, 0. And then continue on the next slide, I go ahead and list the endpoint values. Yes?
So when it's undefined, or when equals 0, those are the critical points?
Critical points are the first 2. Critical points are where f prime equals 0 or where f prime does not exist. Yeah, those are critical points.
Can they also be the maximum minimum? Oh wait, never mind.
Yeah, this whole thing is finding local extrema. That's what this whole thing is. Yeah.
So those are the critical points.
Okay. So continue on the next page.
When you find the critical points,
Yes.
it's that and the endpoints, those are the extrema?
They are all going to be local extrema. Well, okay. Let me just be safe. Let me say this. You take those are the possibilities. Then you take what x value those occur, plug them into the original function to see what value you get.
And whatever's the highest.
And yeah, so then that's what's going on here. So like for example, this one, if we continue with this, exactly what we're going to do. So we had 0, 0, that was an issue because 0, 0, that was where it was undefined, f prime. And then we have our endpoint. So we have the endpoint -2, and then okay, what is the y value? Okay, I'll plug it in the original function. Be careful. And cube root of 4 was the value of that, and then the other endpoint at x equals 3, we have its value. So looking at these 3, here, here, and here. Now to determine the absolute max and the absolute min. Okay, what would be the absolute largest value of the function? Well, 0 is the value when x was 0. Cube root of 4 is the value of the function when x equals -2, and the value of the function is cube root of 9 when x is 3. Okay, of all of these, okay, cube root of 9 is the largest, so that's the absolute max. And then the smallest is, of course, 0, so that's where the absolute min occurs. But if I asked you to list all local extrema, you would just list all 3. These are all local extrema. We would find the absolute maximum min, of course. Okay, what's the absolute max? What's the absolute min? They are all local extrema. Yeah. So there's that one thing that says in the textbook, and it's true, is that all absolute extrema are local extrema.
I thought it was the other way around.
No.
I thought the absolute were the top big and small ones.
Yeah. So they are also local extrema because they are local extrema within their neighborhood. Yeah. So all absolute extrema are local extrema, but not all local extrema are, as we see here, because these are all 3 local extrema. This is a local extremum. This is a local extremum. This is a local extremum. Out of these 3 within this window, within this interval, okay, is there an absolute max within this interval? Is there an absolute minimum within this interval? And I'm going to make it easy and probably just give you guys intervals every time. I'm not going to keep it open the entire domain just to make life easy.
Wouldn't these be considered local because they are within an interval and not over the entire function?
Yes.
So we have bigger ones?
These are all local extrema. Each one of these is a local extrema.
But like the two are local and absolute within that function.
Because even it's still in a set interval, okay, so say it is the absolute, it's still in the neighborhood of the interval, so it would be local as well.
Okay.
That's correct, what she just said. Yeah. Is that clarified? You can ask your question another way or ask it again. I'll try to explain another way, but don't over. But at the same time, don't overcomplicate.
I'll come talk to you.
Okay.
I would say
absolute.
Okay,
If
so
I'm the tallest person in the world, doesn't that also make me the tallest person in my neighborhood? Just my neighborhood?
there you go.
See, that
Beautiful.
makes sense, but here it feels like we're only talking about a neighborhood because you gave us intervals.
It is a neighborhood, but it's tallest there, but it's also tallest overall, put it like.
But.
Okay, so I think now I see where your mind is coming from. Okay, so this 0, 0, if you look at it graphically, that's a really easy way to look at it.
Yeah.
That's a really easy way to look at it. So
I mean,
let's
I don't
go
wanna spend
to,
time on it 'cause I
no,
graph-
no, no, page 189 is a perfect thing. Page 189, look at 189 in your textbook. That is a perfect thing to help you understand this. If you just look at the interval from A to B, and they've actually cut this function off. Do you see how that they're all local? Like, they're all local. Even the local ones that are only local, those are still local max because look at the one that happens at C. Do you see how that guy within his neighborhood, like around that area, he's the top of the hill? There you go, that's when you think of it like that.
See, I can see that, but we were given an interval here. So.
We were given it analytically without a graph.
Yeah.
Yeah, so you gotta,
We were just.
How do we know that they're absolute overall?
Yeah, that's what I'm saying.
okay, the way you know they're absolute is because these are all the local extrema.
So the interval they gave us is where the graph starts and ends, or where the function starts and ends.
Yeah, you only care about the interval.
Okay.
Okay? Even if we
So these are
know,
considered local then?
hey, even if we know this guy goes on forever, even if we know this guy goes on forever up and up and up, we're still cutting it off on the interval that was specified. And the interval that was specified was -2 to 3.
There's a difference.
So it's still called an absolute extrema. It's still called absolute extrema. Even if this function, the entire domain, let's say it goes on forever, either up, down, whatever, doesn't matter. We're only concerned about the interval, so we can state them as absolute.
Okay, that makes sense.
Okay?
Sorry, thank you.
All right, and then once you write all 3 locals, and you say, okay, I've looked at all of them, I know which one's the absolute max, which one's the absolute min, you're done. We have checked all the critical values and the endpoints, we are done.
So, bullet point 2 on the test is checking endpoints and critical values and finding extrema.
Yeah, so back to that. Finding absolute extrema. If I decide to give you a graph, that should be very easy. That's really easy if I give you a graph. So if I give you something like on page 189, I say, okay, within the interval A to B, list all local extrema and then list the absolutes. So you list all the local, which includes the absolutes, and then specifically, okay, just the absolutes are at x equals A and at x equals D. And of course, if you don't know the actual function itself, that's all you can say is that it occurs at x equals A and at x equals D.
What they are, but you know where they
Yeah, if I don't give you the function, you just know where they occur. Yeah. So yes, ask, please. This is the time to ask away, especially this course.
Yeah.
Yeah, I'm planning on doing it tomorrow. Yeah. So page 194, if you want to practice these, finding absolute, you guys grew up with Google. You can quickly find plenty of, you can actually Google these exact ones. You're going to find good practice problems to do, but you also have your textbook on page 194. If you want to look at some of those, I would look at maybe 17 and 18, because I'm not going to give you, you should know the derivative of ln. You should know that, but I think I'm going to just keep it simple. You know the derivative of ln, derivative of e to the x, and
Oh, yeah. I know something, that's exciting.
but I'll probably just keep it simple, like 17 or 18. So if you want to practice one, 17 is a good practice. It may have actually already been a homework, but you can always, okay, act like I've never seen this problem before. I'm going to do 17 on 194 from start to finish. See how well I do, and then check your work. That's a perfect way to practice. Don't look at any notes. Just, okay, can I do number 17 from start to finish? Yes, I can. I did it perfectly. I'm probably good for tomorrow. That's the way you want to do it. That's the best way to practice, I think. So that is 4.1. Knowing the definitions, I give you all the definitions or the theorem except a blank spot. Be able to fill it in. And then of course find extrema. So now 4.2. 4.2. 4.1. This is 4.1. Now 4.2, mean value theorem. Again, as far as the theorems and the definitions and the corollaries, and there are several corollaries. There are 3. There are 2 definitions, and then there is the theorem. So let me read the theorem out loud to just, this also helps us review, because that's what we're looking at. Mean value theorem for derivatives. If y equals f of x is continuous at every point of the closed interval a to b, and blank at every point of its interior a, b, then there is at least one point c and a, b at which blah 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 given. So you see what I did there? Know that it needs to be both continuous and differentiable. Now, the only reason, this is a good detail I want to point out, the only reason that they didn't just say if y equals f of x is differentiable, because remember, differentiability implies continuity, is because of the whole brackets versus parentheses, which is good because they're being very particular. But do know that differentiability implies continuity. If I say that a function is differentiable, then it is continuous for every part of its domain of the original function. Don't focus on that right now, though. I just want to. That's not your focus for tomorrow's test, but that's something that's good to know in general. So understand. So theorem 3. Okay, now theorem 3. Remember what that talks about? Talks about if we do have a situation where it's continuous and differentiable, then we at some point, and a good just 196 to get an idea. You see on figure 4.10, you clearly see where the secant line, the slope of that secant line from A to B, there is going to be some other tangent line that has that same slope. That's all that it says for the mean value theorem. And Rolle's theorem is the one that specifically just says if A and B, if f of A equals f of B, and that equals 0, then you're going to have some point where f prime is equals 0. It's basically just a specific version, or a specific example you could think of the mean value theorem. Rolle's theorem is on 196 on the left, which is actually kind of interesting that this guy is ironic that he is known today only for an unintended contribution to a field he tried to suppress. So this guy was not a fan of calculus, but now he's known for this theorem within calculus, even though he didn't like it. He distrusted it, yeah. Well, you got to think in history, there were times when someone of a nation, a ruler of a nation, would say pi equals 3, and if anyone says anyone different, you're going to get killed. Because I'm sick of this 3.1. Societies were strange back then. You had, yeah. Yeah, so there was a whole argument about pi for many, many years.
There was? Like, that was an actual...
Yeah, there's actually drama in math, yeah. Yeah. 0 was an issue for a long time as well.
After the AP Calc exam, can you create a soap opera over the history of math? That would be so much fun. We can put on like this thing. Should we be expected to write definitions for this, like 4.1?
You don't have to write a definition.
No, but
You just have to fill in one blank piece.
So that 4.1 and 4.2?
Yes.
Okay.
Okay. So let's continue with that part. So that, okay, and differentiable. Definitions for increasing function, decreasing function.
But what's a corollary like that? No, but like, I don't get it. Like, what is that?
It's like an extension off of something. It's like, oh, okay, we make this statement, so we can make this corollary to it. There you go. It correlates to that. There you go. So increasing function, decreasing function. So let f be a function defined on an interval I, and let x of 1, x of 2 be any 2 points in I. F blank on I if blah blah blah, and f blanks on I if blah blah blah. Corollary 1, if f be continuous on a to b and differentiable on a to b, 1. If f prime is greater than 0 at each point of f of b, then f blanks on a to b. If f prime is less than 0 at each point of a to b, then f blank on a to b decreases. Very simple. You can see the answers like in the title too. So for some of these. Next one, corollary 2. Functions with f prime equals 0 are constant. If f prime of x equals 0 at each point of an interval I, then there is a constant c for which f of x equals c for all x in I.
That was a thing where you showed us.
It basically, if you think about if f of x equals some constant, then f prime of x equals 0. Just the other way, instead of the other way around, which makes sense.
The derivative is only 0.
Yeah, the derivative of constant is always 0. So, yeah. So functions that have f prime equals 0, those functions are constant. That's all it says.
That's
Yes.
Are there going to be grid functions applying to the mean value theorem on the test?
No.
If so, like you, or even if we're not.
Okay. I want to say no. I'm going to say no. So, okay, so you don't know right now, but moving forward, you do need to become comfortable with what, okay, the derivative of sine, cosine, and tangent. Those 3 for right now. Eventually, you have to know all 6.
we need to know corollary 2.
So the next thing, corollary 3. Functions with the same derivative differ by a constant. If f prime of x equals g prime of x at each point of an interval I, then there is a blank such that f of x equals g of x plus c for all x and I.
So you can have the same derivative of both, there's just a different difference in the cosine.
Mm-hmm. Like the derivative of sine of x, and then outside of that plus pi over 2 is the same thing as the derivative of sine of x plus negative pi over 3. Right? Because you take the derivative of each, the constant goes to 0.
Why would they add the plus, like, why would they add the constant to g of x? It could be like f of x.
Because it doesn't matter where you place it. Yeah. Antiderivative, a function f of x is an antiderivative of a function f of x if f prime of x equals f of x for all x in the domain of f. The process of finding the antiderivative is antidifferentiation. So I might either leave both of those blank or one blank, but both blank would not be tough either because you know it's talking about the antiderivative. That was mentioned once during one of our lessons.
Yeah.
It's a complicated
But for right now, just know that antidifferentiation is going to be the next main part of calculus. Calculus is usually divided into two areas. You have differentiation, and you have antidifferentiation.
Do we have to get through this entire book before the test?
Not necessarily,
Wait.
because I know we skipped one section because I've never seen inverse trig used on it. So if I do see it used, because I'm looking at a lot of practice exams, then we'll go over it, but I have never seen one. I've looked at several in the past. I've never seen them used, so I skipped over that one. And then actually knowing how to do a problem involving mean value theorem. So exactly like the homework, basically. Alright, I want you to first state whether or not the function satisfies the hypothesis of the mean value theorem.
And it only does it if it's.
And you're gonna have that. You're gonna have it on your test too, right? Because you just had that with the blank that you filled in. If it does, find each value on C in the interval that satisfies the equation. So if it doesn't satisfy it, you're done. You don't have to do part B. This is on page 202, guys, for the homework that you looked at.
Whether it satisfies the mean value theorem by telling me whether it's differentiable or not.
Yeah, so for it to satisfy, again, you're going to have it on your test. You'll have one blank that you fill in. But it needs to be not only be continuous at every point, but it also needs to be differentiable at every point of its interior.
Sounds like fun.
Yep.
So the mean value theorem is basically, it has to be differentiable.
Are we gonna have any piece lessons ones
I don't think so.
Still,
But again, everything, a lot of the stuff that we're avoiding, eventually you're going to have to solidify it at some point.
No, I get
that's
that.
at some point. I'm good at procrastination, trying to show you my skills.
so you guys pretty much have the rest of the time. If you want to look at any problems together, we can pick one and look at it and go over it together.
Yeah.
Does that sound good? Mean value theorem? Yes, you can go to the restroom, yeah.
No, you must continue your street.
Yeah.
Have fun.
Alright, so mean value theorem. Yeah. I think have we already done 1 and 2?
Let's do 4. I don't think we've done that one. No, that's
Yeah, that's a
No, no,
piecewise.
discussion on that.
Absolute value is piecewise.
Yeah.
There we go, we can do 3.
That's a good one. I want to walk through with an entire problem.
Okay, so number 3. Let me actually finish this list here. Mean value theorem problems. Page 202, number 3. So number 3 says that f of x is equal to x to the 1/3 power on the interval -1 to 1. Okay, so of course they have to specify an interval because okay, what do we want the average rate of change to be? So they have to give you an interval. They'll give you an interval. So before we go to part B, actually let's make sure the answer is yes. Let's see if it's yes. State whether or not the function satisfies the hypothesis, the mean value theorem on the given interval, which you'll have on your test except for one missing piece. So you say, okay, look at the theorem. If y is continuous at every point of the closed interval and differentiable at every point if it's interior. Okay, well let's see. Let's actually do f prime of x. See what it looks like. If I do f prime of x, I'm going to have 1/3 drop to the front. This is dropped down just using the power rule, and you get -2/3, which can be rewritten so that it's a positive exponent. You'd have 1/3x to the power of +2/3. So is there any situation, because think about what you learned in the previous section 4.1, where are there situations where f prime doesn't exist, which is therefore wouldn't be differentiable when x equals 0. So at x equals 0, f prime does not exist. So this does not satisfy the mean value theorem because this occurred in our interval.
I have a question.
Yes.
So it's always f prime when you check it?
Okay, so what I'm checking for is the fact that it needs to be continuous and it needs to be differentiable. Okay, well here's the
After
thing.
you take the
Just check for differentiability. Again, they were very specific in breaking that because one is like, okay, parentheses versus brackets. Okay, but do know that differentiability implies continuity.
Okay.
So as long as you're testing a value that's in between, then you're good. So knowing what differentiability means, like the warm-up, okay, well, where f prime does not exist, or the derivative does not exist, that's an issue where it's not differentiable. So if we find a situation, yeah, okay. And this is going to be, Rebecca, this is going to be vertical tangent line, or a cusp, or a corner, or discontinuity. We know it's not. I know it's not discontinuity because I have an idea what this guy looks like.
Yeah. No, I get
So it's one of those other 3: corner, cusp, or vertical tangent. This guy actually ended up being a vertical tangent. Yes.
Can we do number 9 really quickly?
All right. Number 9. So the interval a to b is given. Okay, equation for the secant line. So this is something that if I did, it would probably be a bonus. So definitely considering looking at it. So I already heard Grace say it's discontinuous. Yeah, so we look at it, where is it discontinuous right off the bat?
Zero.
When x equals 0. Okay, now does that fall within the interval? No, so we don't necessarily have, we're not done. Because, right, it's, the mean value is within this interval. Okay, so it may be continuous and may also be differentiable within those points. So actually using the mean value theorem. So the secant line. Well, what is the average rate of change? That would give us the slope of the secant line. So we're going from 0.5 to 2. I know we're running out of time, so I'll try to move quickly. F of 2 would be equal to 2.5. F of 0.5. I think this one actually ends up where the Rolle's theorem is actually going to apply here, I think, because they end up being the same value. F of 0.5 is, 1.5 or 2.5? 1 divided by 1/2 is 2. 2 plus 1/2 is 2.5, right? Be careful. Yeah, we've done this one. So then we have, okay, so to find the slope of the secant line, or the average rate of change, okay, so we have 2.5 minus 2.5 over 2 minus 0.5. So this is going to have the slope of 0. So that's the slope of the secant line. Right? Because what we did, we just found the average rate of change from A to B. So that would be the slope of the secant line. Now to find the equation for it, you guys can use what? Point slope form. You can pick a point. You pick 2.5 as your point, and use this as your slope, and use your point slope form. For those of you that really want to use y equals mx plus b, you can do that as well. Find b, then rewrite it where y and x are the ones left as blanks.
I have a question.
Yeah.
So does that mean the secant line is horizontal?
Yeah. Yeah, this one happens to be where Rolle's theorem comes into play. We're running low on time, so just again, to find, doesn't matter how you find the equation line, whether it's you like point slope form, you like slope intercept form, and then a tangent line to f in the interval that is parallel to AB. So now you have to find f prime of x and set that equal to 0, right? So set f prime of x equal to 0, and that'll tell you the point C where the tangent line has the same slope as your secant line.
See, when I did it, though, it came out to 0 equals 0.
Wait, what? Set that?
Fine, at prime
Yep.
of x
So-
equals 0 because 0 is the slope.
So that can be 5.2 where
F prime of x we have as 1 plus, this is x to the negative 1, so I think about negative x to the negative 2.
Oh, I did it wrong. That's why I said that.
Set this equal to 0, right?
Solve for it.
We're talking about this 0 here,
Oh, solve for it.
right?